Alright, welcome back. In this video, we begin looking at how to make inferences about a population in the context of stratified random sampling. Here's an overview of what we'll be looking at in this video. Now there are two main sections. In the first section, we look at how to make inferences about the individual strata comprising a stratified population. In particular, we'll come up with unbiased point estimators of the means and the variances of the individual population strata. Once we've done that, we'll use that information to come up with confidence interval estimators of the individual strata means. We'll also look at how to compare the strata means. Now our focus will be on pairwise comparisons, and we'll make these comparisons using confidence interval estimators of the difference between the strata means that are being compared. Next, we'll use the unbiased point estimators of the strata means to come up with an unbiased estimator of the mean of the overall population. We'll also come up with a confidence interval estimator of the overall population mean. So we've got a lot to do here. Let's jump in. Next, what we need to do is talk about calculating summary statistics for the observations that have been selected from each stratum. And so let y1j, y2j, and so forth up to y sub little nj comma j denote a simple random sample of size little n sub j from stratum j of the population. Let y bar j and s squared j be the mean and variance of that sample. All right, so we have the formulas here, the usual formulas for the sample mean and the sample variance. All right, these are the sample mean and variance from the jth stratum. And so once we have that, then we can look at inferences for means of population strata. So we're going to focus first on making inferences about the various strata, and then we will look at making inferences about the population as a whole. And so let's first talk about estimating the parameters of the population strata. Now, based on results obtained for simple random sampling that we covered in the last module, we know that an unbiased estimate of mu sub j, the mean of the jth population stratum, is given by the mean of a sample that has been selected from that stratum. So that mu hat sub j, the unbiased estimator of mu sub j, is equal to y bar j, or y bar j dot, which is the, this is y bar j, that's a period there at the end of the sentence. So y bar j, which is the mean of the sample that has been selected from stratum j. In addition, an unbiased estimator of sigma squared sub j, the variance of the jth population stratum, is given by this expression. All right, so notice that it's not just the variance of the sample that's selected from stratum j, but it's equal to cap n sub j minus 1 over cap n sub j times the variance of the sample that was selected from stratum j. And so this result comes directly from what we learned in the module on simple random sampling. And so we have a simple random sample from this stratum, and from this perspective we can think of this particular stratum as a population in and of itself, right? And so we have a simple random sample from this particular stratum, and so the estimates for the mean and the variance of that stratum follow directly from the formulas, the results that we obtained in the previous module on simple random sampling. All right, now let's talk about the variance and the standard error of the estimator of the stratum mean. Now, what does that mean? Well, let me go back one slide. This quantity here, mu hat sub j, that's the unbiased estimator of the stratum mean. And so what we want now is to think about the variance of that estimator. And so that's what we're doing on this next slide. And so the variance of the sampling distribution of the estimator of mu sub j, the mean of the stratum j, is given by this expression. So the variance of mu hat sub j, in other words, sigma squared sub mu hat sub j, is given by this formula here. Now, notice that this is expressed in terms of the stratum size, cap n sub j, the sample size, little n sub j, and the stratum variance, sigma squared sub j. Now, this is a direct result from the results that we obtained in the previous module on the variance of the estimator of a population mean using a simple random sample. So this is the same exact formula. The only difference is that we have to subscript cap n, little n, and sigma squared because we're talking not about the entire population, but we're talking about a particular stratum. Okay? So once we have the variance of mu hat sub j, to find the standard error, the true standard error of mu hat sub j, or at least an expression for it, right? Then all we have to do is take the square root of this, and so that's what we're doing down here. And so the standard error, the true standard error of mu hat sub j, in other words sigma sub mu hat sub j, is equal to the square root of this quantity here, cap n sub j minus little n sub j, over cap n sub j minus 1, times 1 over little n sub j, times, and then notice here that I've factored out the sigma squared sub j outside of the square root sign, and so when I do that, it's no longer squared because I took the square root. All right, if you wanted to, you could keep that variance inside the square root, and so that would be, you would have sigma squared sub j inside, but you can do it either way. Okay, now the problem is, let me go back. The problem with these formulas is that we don't know the population, or the stratum variances. We don't know the population variance, the overall population variance, and we don't know, in most cases, will not know the true stratum variances, and so we can't calculate the variance nor the standard error of mu hat sub j exactly. And so what we have to do, clearly, is we have to come up with estimates for the variance and standard error of mu hat sub j. And so that's what we're doing on the next slide, estimation of the variance and standard error of the estimator of a stratum mean. Now again, I want to point out here that so far there's nothing new here. Everything that we're applying is based on what we did back in the previous module on simple random sampling. What we're doing is treating each stratum as its own separate population, at least that's one way to think about it, in order to come up with these estimators and the standard errors of the estimators. All right, and so in order to get the estimator of the variance of mu hat sub j, what we need is the estimated variance of the jth stratum. All right, so that's given by sigma hat squared sub j, and we just plug that in to this formula on the previous slide. Okay, and so sigma hat squared sub mu hat sub j, the estimated variance of mu hat sub j, is given by either of these expressions. All right, and so you can express this estimated variance in terms of either the unbiased estimator of the jth population stratum, sigma hat squared sub j, or you could express it in terms of the sample variance from the jth stratum. All right, so both of these formulas are probably good to have in your notes, and on a note sheet or something for when you're doing its assignments and an exam and things like that. So once we have the estimated variance of mu hat sub j, to get the estimated standard error of mu hat sub j, again, what do? Well, we take the square root. All right, so the corresponding estimator of the standard error of the estimator of the population mean is given by these expressions down here. These are equivalent. Again, you can use whichever one is most convenient. Now again, let me just go back up here to this previous formula, the estimated variance of mu hat sub j. That is an unbiased estimator of sigma squared sub mu hat sub j. All right, so that's an unbiased estimator of the variance of mu hat sub j. When we take the square root, we get the estimated standard error of mu hat sub j, but that is not an unbiased estimator of sigma sub mu hat sub j. Right? It's the estimated variance. It's the estimated variance that is the one that's unbiased. Now, once we have the estimated standard error of mu hat sub j, then we can compute the estimated approximate 95% margin of error of the estimator of the stratum mean. All right, so that's quite a mouthful, isn't it? The estimated approximate 95% margin of error associated with mu hat sub j. And so it's estimated because we have a sigma hat here, a sigma hat sub mu hat sub j. So it's that hat right there that makes this an estimated quantity, and it's approximate because we're using 2 instead of the 1.96. So this is an estimated approximate 95% margin of error associated with mu hat sub j. And so what you can do is calculate the estimated standard error using either of those two formulas and then just hit it with 2, and then that will give you the estimated approximate 95% margin of error. And so once we have the point estimate of mu sub j, that point estimate being mu hat sub j, and its estimated approximate margin of error, then we just subtract that margin of error from mu hat sub j to get the lower end point of a confidence interval, and add that margin of error to the point estimate to get the upper end point. All right, and so that is what we're doing here. So again, whenever we're constructing these confidence intervals using a procedure that's based on normality or that kind of thinking, right? Then the way that we get the confidence intervals is to start off with a point estimate, in this case mu hat sub j, and then go a distance to the left and that same distance to the right to get the left and or the lower and upper end points of the confidence interval. And that distance that we go is that margin of error. All right, next what we're going to do is look at inference for the overall population mean using a stratified random sample. So the first thing we need is an estimator of the overall population mean, a point estimator in particular. And so recall that the overall population mean mu can be expressed in terms of the stratum means and the stratum sizes according to this formula here, 1 over cap n times the sum, j going from 1 to cap l, so we're summing up over all the strata. And what are we adding up? Cap n sub j times mu sub j. So with that representation, it becomes very easy to come up with a point estimator for mu. We'll denote that point estimator by mu hat, and so that's given by replacing each of the unknown each of the unknown stratum means by the estimator of the stratum, each stratum mean. And so that's the sample mean from each stratum. And so mu hat is equal to this. It's a weighted average. All right, 1 over cap n times the sum, j going from 1 to cap l, of the product of the products of the stratum sizes times the means of the samples selected from those strata. Now notice that in order to compute this, we're going to have to know the stratum sizes, obviously. Okay, and then once we have that point estimator for the overall population mean, then we're going to eventually want to compute a margin of error associated with that point estimate, and also, and for the purposes of constructing a confidence interval for the population mean. But to do that, we first need to know the form of the variance and standard error of that point estimator. And in particular, we need to know the form of the variance and the standard error of mu hat. And so it can be shown. Now this is new. This is not. It's based on what we did in in simple random sampling in the previous module. It's based on the estimators that we've just talked about in this lecture, and it's also based on the fact that the samples from the various strata are independent. All right. So when that's the case, well, and let me back up. In order for these formulas that I'm about to show you to be valid, then those samples from different strata have to be independent. So that's why we really emphasized that when we talked about it. So given that, the variance of the sampling distribution of mu hat, the point estimator of mu, is given by this expression, this sum. So it's a sum, j going from 1 up to cap L. So we're computing some things for each stratum, and then we're adding those values up. All right, and so we have the ratio of the stratum size to the overall population size squared, and then we multiply that against cap n sub j minus little n sub j over cap n sub j minus 1 times 1 over little n sub j times the variance of the jth stratum. All right, so it's not too complicated, but it's more complicated than it was for the simple random sampling situation. Once we have the variance of mu hat, we can take the square root of that value to get the standard error of mu hat. And so this is sigma sub mu hat is just the square root of that same sum. Now again, if we don't know the population variances, the stratum variances, then we can't calculate the variance and standard error of mu hat exactly. And so it will, these quantities will need to be estimated. And we do that by plugging in point estimates for the stratum variances. All right, and so this is what we're doing on this page to come up with estimates for the variance and the standard error of mu hat. And so the one way to express the estimated variance of mu hat is in terms of the sample variances. All right, and then once we have this expression, then we can take its square root, right, to get the estimated standard error of mu hat. Now, you could also express these formulas in terms of the unbiased estimates of the stratum variances. All right, and so in fact, you might want to write those down and just make sure that you can come up with those formulas on your own. All right, but these formulas will suffice. Once we have the estimated standard error of mu hat, then we can multiply that by 2 to get the approximate 95% margin of error that is associated with mu hat, the unbiased estimator of the overall population mean, and that is given by this expression here. Now, once we have our point estimator of the overall population mean and its estimated approximate margin of error, then we can use those two quantities in the usual way to come up with the approximate 95% confidence interval estimate for the overall population mean. Right? So mu hat minus plus, and then the margin of error associated with mu hat. So let's look at an example. An advertising firm is interested in determining how much to emphasize advertising in a certain county. To do this, the firm decides to construct a sample survey to estimate the average number of hours per week that households within the county watch television. The county contains two towns, Town A and Town B, and also a rural area. So it's got 3 areas, 2 towns, Town A, Town B, and then a rural area. Now, Town A is built around a factory, and most households contain factory workers with school-aged children. Town B is an exclusive suburb of a city in a neighboring county and contains older residents with few children at home. Now, there are 155 households in Town A, 62 households in Town B, and 93 households in the rural area. The advertising firm has budgeted enough money for the survey to interview 40 households and has selected to use stratified random sampling to do the sampling process. To do this, simple random samples of size 20, 8, and 12 are selected from Town A, Town B, and the rural area, respectively. Now, the reported television viewing times in hours per week are given below. And so we have the data values, the number of hours spent watching television per week for Town A, given here, for Town B, given here, and then in the rural area, given here. So this is the raw data, right, for our analysis. We have 3 areas, the population of households has been partitioned into 3 strata, all right, and then we have selected a simple random sample from each of the strata. And they've been selected in such a way that they are stochastically independent of each other. Now, notice here that the stratum sample sizes are not the same, but they can be different. In fact, in most cases, they probably will be different. Okay, so what are we to do here? Well, for each location, for each of the 3 areas, Town A, Town B, and the rural area, estimate the average number of hours spent watching television per week and compute the margin of error associated with each estimate. In addition, construct an approximate 95% confidence interval estimate for the mean for each location. The next question is, are there differences across the three locations in terms of the mean number of hours spent watching television per week? And so we want to evaluate the evidence that exists in the data. And then finally, estimate the mean number of hours spent watching television per week across the entire county and compute the margin of error associated with this estimate. Finally, construct an approximate 95% confidence interval estimate of that overall population mean. Okay, so here we have summary statistics for the three strata. We have the stratum sizes here. So these would not be considered statistics. These are actual stratum values. So we have 150 households in stratum 1, which is town A. We have 62 households in stratum 2, which is town B. And then we have 93 households in the rural area, or stratum 3. We have a simple random sample of size 20 from stratum 1, a simple random sample of size 8 from stratum 2, and a simple random sample of size 12 from stratum 3. And then summarizing the data, we have the sample means here in this column, we have the sample standard deviations, and we have the sample variances. All right, notice that there are a total of 310 households in the entire county, and the overall sample size is 40 households. All right, so let's look first at stratum 1. So the sample mean for stratum 1, or the mean of the sample selected from stratum 1, was 33.9 hours, all right, per week, and so that is the estimate for the mean number of hours spent watching TV for that particular stratum. Now, in addition to this point estimator, we want to construct or calculate the approximate margin of error associated with that point estimator, and that is given by sigma hat sub mu sub hat 1. All right, and that is given by this formula here. All right, and so we take the stratum sizes, or the stratum size, the sample size, and the sample standard deviation, all right, and plug those in, and we get 1.241 hours per week. So that is the estimated standard error associated with this point estimate. Now, once we have that estimated standard error, we multiply it by 2, right, to get our approximate 95% margin of error associated with mu hat sub 1, and that turns out to be 2.482. Once we have the point estimator, 33.9, and the margin of error associated with that point estimate, then we subtract the margin of error from the point estimate to get the lower endpoint, add the margin of error to the point estimate to get the upper endpoint. And so we can say that we are approximately 95% confident that the average number of hours spent watching television per week in this first stratum, town A, is somewhere between 31.42 hours per week and 36.38 hours per week. All right, next for stratum 2, we did the same kind of thing, used those summary statistics to come up with a point estimate for the average number of hours spent per week watching television in this stratum, 25.125 hours per week. The estimated standard error of mu hat sub 2 is given by this expression, so 5.0302. We multiply that by 2 to get the approximate 95% margin of error associated with this point estimate. And so that gives us 10.0604. And then finally, once we have the point estimate and the margin of error, we can construct the approximate 95% confidence interval for mu sub 2, which ranges from 15.0646 hours per week up to 35.1854 hours per week. And so we can say that we are approximately 95% confident that the average number of hours spent per week watching television in the second stratum, which is town B, is somewhere between 15.06 hours per week and 35.19 hours per week. And then finally, we do the same thing for the third stratum, which is this rural area. And so the point estimate for the average number of hours spent per week watching television in the rural area is 19.0 hours. the approximate 95% margin of error associated with that point estimator is 2.522 hours per week. All right, that's the estimated standard error of that point estimator, and then we multiply that by 2 to get the estimated margin of error associated with mu hat sub 3. So the approximate 95% margin of error of mu hat sub 3 is equal to 5.044. And so the corresponding approximate 95% confidence interval for mu sub 3 ranges from 13.96 hours per week up to 24.04 hours per week. All right, next, we need to estimate the overall population mean, the overall average number of hours spent per week watching television for all or across all households in this county. All right, and so we compute this estimate, mu hat, according to this formula. All right, so again, this is a weighted average of the means of the samples from each of the 3 strata. All right, the weight factor being the stratum sizes. And so when we do this calculation, we get 27.675 hours. So our point estimate for the average number of hours spent per week watching television across the entire population, this entire county, is 27.675 hours per week. All right, but that's not all we want. We also want to understand and quantify the variability associated with that point estimator. And so to do that, we need to first calculate the estimated variance of mu hat. Once we have that, then we can take the square root to get the estimated standard error of mu hat. And then we can multiply that estimated standard error by 2 to get an approximate 95% margin of error associated with mu hat. So to compute the estimated variance of mu hat, we have to calculate this kind of a product for each of the strata in the population, and then we have to add those products up. And so in this case, we have 3 strata, all right, and so we have to calculate these products for each of the 3 strata. Now, be very careful. It's the more calculations you do by hand, the more susceptible you are. The greater opportunities there are for calculational errors, and so we just have to be very careful that not only do we do the calculation correctly, but just write it down correctly. We have to be very methodical and very careful when we write these formulas down. And then once we have it written down correctly, and my recommendation would be to write these things down and then compare them, go back and compare them to the general formula. And then once you've convinced yourself that you've written it down correctly, then very carefully plug these values into the calculator. All right, and so once we do that, in this particular case, then the estimated variance for mu hat is equal to 1.9695, and the units on this, because this is an estimated variance, would be hours squared. Okay, so once we have this estimated variance, then to get the estimated standard error, all we have to do is take the square root, all right, which gives us 1.4034. So that is the estimated standard error of mu hat. Once we have that, then we multiply it by 2 to get the estimated margin of error associated with mu hat, which is equal to 2.807. And so once we have that, then we can use the point estimate along with this margin of error to construct the approximate 95% confidence interval estimate for mu, the overall population mean. That interval ranges from 24.868 hours per week up to 30.482 hours per week. And so we can say that we are approximately 95% confident that the average number of hours spent watching television per week for the whole county is somewhere between 24.87 hours and 30.48 hours. Okay, so here are the summary of the results for the individual strata. All right, we have point estimates for the strata means. We have point estimates of the margin of errors associated with those strata means. And then we have the corresponding approximate 95% confidence intervals for the individual stratum means. And then down below, we have the same quantities, but for the overall population. So we have the estimate of the overall population mean, an estimate of the margin of error associated with that estimated mean, and then the corresponding approximate 95% confidence interval for mu, the overall population mean. Now, based on those results, based on that summary, can you conclude whether any differences exist among the stratum means? So if we go back and look at this, notice that, so the question would be, does it look like there could be differences between the means of the individual strata, or are they the same? And so one approach would be to take these individual, these confidence intervals for individual means and look for overlap, and you can see that there's a lot of overlap between really all of these, each of these three intervals. Okay, so that's one way to do it. So again, this could be addressed by constructing, well, let me back up. So that's one way to do it, but that's not the best way, all right? A better way would be to construct confidence intervals for the difference between pairs of means using a procedure that extends the two-sample procedure you learned in your introductory methods class by taking into account the stratified sampling method that has been used to obtain the data. Remember that the way that we select the data, the way that we sample the population or perform the experiment determines the appropriate method of analysis. And so in order to construct confidence intervals for differences of means, we can't just use the formulas that we learned in our first methods class, because again, those formulas are based on the assumption that IID random sampling has been used. But that's not the case here. In this case, we have stratified random sampling, and in particular, within each stratum, we've selected a simple random sample. And so that whole sampling mechanism has to be taken into account in order to properly construct confidence intervals for the differences between the means of two strata. And so let's look at how to construct an approximate 95% confidence interval estimate for mu1 minus mu2. All right, and so it would be, again, the way we do this is we start off with a point estimator, and then we go a distance to the left and to the right. From that point estimator, an amount equal to the approximate margin of error associated with that point estimator. And so the point estimator would be mu hat 1 minus mu hat 2. Again, what we're doing here is we're wanting to construct a confidence interval for mu1 minus mu2. And so we start off with a point estimate of that. So mu hat 1 minus mu hat 2. And then we have to know the margin of error, right? And in particular, the margin of error of mu hat 1 minus mu hat 2. Well, the margin of error, the approximate margin of error associated with mu hat 1 minus mu hat 2 is 2 times the estimated standard error of mu hat 1 minus mu hat 2. And the estimated standard error of mu hat 1 minus mu hat 2 is given by this expression here. And so notice that we have an exponent up here of 1/2, and so we're taking the square root of this quantity inside the brackets. Okay, so make sure that you write this down. This is not in your note packet, I don't think. If it is, fine, but if it's not, be sure to write it down. All right, so this would be the estimated standard error of the difference between the estimated strata means, mu1 hat minus mu2 hat. Okay, so our point estimate for the difference between the means of strata 1 and 2 would be mu hat 1 minus mu hat 2, 33.9 minus 25.125. That gives us an estimated difference of 8.775. Okay, and then we have to calculate the estimated standard error of that point estimator. And I see here that, I want to point this out to you, I see here that when I scanned this, the scanner didn't capture all of this. So there's this 15.245 is squared, okay? And then we also have to, there's an exponent of 1/2 out here, so we would have to take the square, and that's why we've got this square root here. So just make sure that as you're looking at this, you realize that a little bit got cut off there. I apologize for that. Okay, so again, to get this estimated standard error, we're just plugging into this formula here. All right, and when we do that, we get an estimated value of 5.1810. To get the approximate margin of error associated with mu hat 1 minus mu hat 2, we multiply this estimated standard error by 2. All right, so we get 10.3620. And then it's that value that we subtract from and add to this point estimator to get the approximate 95% confidence interval for mu 1 minus mu 2. And so when we do that, we see that the approximate 95% confidence interval ranges from negative 1.59 hours per week up to 19.14 hours per week. And so notice that that interval contains 0. And because, or since that 95% confidence interval includes 0, we can conclude that there is insufficient evidence at the 0.05 level of significance, or equivalent to the 5% level of significance, to conclude that mu 1 is not equal to mu 2. All right, next let's compare the means of strata 1 and 3. So to do this, we will construct an approximate 95% confidence interval estimate for mu 1 minus mu 3. We'll use the same kind of procedure. We'll first calculate a point estimate of mu 1 minus mu 3. That's given by mu hat 1 minus mu hat 3. All right, and that estimate is 14.9 hours. Then we need to calculate the estimated standard error of that point estimate. And using this formula, you can see here that that turns out to be 2.811 hours. We multiply that estimated standard error by 2 to get the estimated margin of error associated with mu hat 1 minus mu hat 3. And that estimated margin of error is 5.622 hours. And then finally, once we have that, then we can compute the approximate 95% confidence interval estimate for mu 1 minus mu 3. And we see here that this interval does not contain 0. We're approximately 95% confident that mu 1 minus mu 3 is somewhere between 9.28 hours and 20.52 hours. And so since the 95% confidence interval estimate does not include 0, there is sufficient evidence at the 0.05 level of significance to conclude that mu 1 is not equal to mu 3. And then finally, we compare the means of strata 2 and 3. We do this via a confidence interval for mu 2 minus mu 3. The estimated difference between mu 2 and mu 3 is 6.125 hours. The approximate the approximate standard error of that point estimator is 5.6270 hours. We multiply that by 2 to get the approximate margin of error associated with that point estimator. This turns out to be 11.254 hours. And then finally, we use those to construct an approximate 95% margin of error associated with mu 2 minus mu 3. And that interval ranges from negative 5.13 hours up to 17.38 hours. And so since the 95% confidence interval does include 0, there is insufficient evidence. There's not enough evidence at the 0.05 level of significance to conclude that a difference exists between the average number of hours spent watching television per week for strata 2 and strata 3. Now let's look at another example, a related example. In the previous example, what happens to the quality of the inference in terms of precision of estimation if in the data analysis we ignore the stratification and instead treat the data as if simple random sampling had been used? What happens if we use the estimation procedure based on sampling from an infinite population? So in other words, we know that we have selected a stratified random sample from this population. And we've come up with some results. What happens if we ignore the stratification and do one of two things? We either use simple random sampling, or we even ignore the fact that we were sampling without replacement, and we use a procedure that's based on sampling with replacement. Well, let's take a look. So what happens if we ignore stratification and use procedures based on simple random sampling? All right, well then in this case we have the following values. Cap n is 310, the overall sample size is 40. We have the sum of the x's, 1107. The sum of the squared x is the uncorrected sum of squares, being 35,629. We have the sample mean here, the sample standard deviation, and the sample variance, and I'll let you calculate these and verify these on your own. And so using those values, the estimate of the overall population mean, which would be given by the overall sample mean, is 27.675 hours. Now, that's the exact same value we got using stratified random sampling procedures. Now let's look at the estimator, the estimated standard error of that quantity. And so using the formula from simple random sampling, the estimated standard error would be 1.6696. Multiply that by 2, we get the estimated approximate 95% margin of error associated with mu hat being 3.3392. And if we compare that to the margin of error that we got when we used the procedure for stratified random sampling, and if we compare this using the relative error, then we see here that we get a relative error of 19%. And so what this is telling us is that ignoring stratification, using formulas based on simple random sampling alone, result in a margin of error that is 19% larger than what it should be. And so, what's the impact of that? Well, if we think about constructing then a confidence interval for the overall population mean, that confidence interval is going to be too wide. It's going to be 19% too wide. So precision is therefore diminished, and the quality of the inference is degraded or diminished when we fail to take into account that we have used stratified random sampling. When we ignore that information, when we throw that information away, and we use the incorrect formulas, then we're really shooting ourselves in the foot, all right? Because we are degrading or diminishing the precision that is available to us in the data if we would only use it in the correct way. Now, what if we, instead of using samples for just simple random sampling, but we completely ignore the fact that we were sampling without replacement and use formulas that are based on IID random sampling, so using procedures that you learned in your first methods course. Then doing that, the estimated standard error of mu hat is 1.789. The margin of error would be 3.578. And then the relative error in that margin of error compared with the correct margin of error, which is 2.8068, that relative error would be 27.5%. And so therefore using the standard formulas based on sampling from an infinite population or from a finite population with replacement, the resulting margin of error would be overstated by close to 30%, 27.5%. All right, and so the resulting confidence interval for mu would be quite a bit larger, quite a bit wider. All right, and remember that wider confidence intervals provide less information to us than shorter intervals. So we're seeing here the importance of properly taking into account the way in which a population has been sampled. And in particular, if we have selected a stratified random sample, then we can't ignore that stratification in the analysis. We have to take that into account in order to properly take into account all the information that is available in the data. If we don't take that stratification into account in the analysis, then we're really throwing away information, and we've got hypothesis tests that are less powerful, and we have confidence intervals that are less precise.